Hello there. Last time we talked about the components of the artificial neural network. Today we're going to dig deeper into how to train a deep neural net. So here we go. So training deep neural net. The training of the neural network typically involve around 4 different objects. Remember, anytime someone asks you about training a neural network, they have to have 4 objects taken care of. Number one is the input data. This includes feature and corresponding label or values. You need to have a label, layers, or the architecture design of the network. How many layers there are, how many depth of each layer, how do all these layers combine into the network. You need a loss function, which defines the feedback signal used for training. And finally, you need an optimizer, which determine how the training proceed or how to learn the network parameters. So you need all these 4 things, and to determine these 4 things before you start the training part of the neural net. And to look at the overview of the training, you can see here the input go in with the data transformation from layer to layer. Each of the layer associate with a weight. Let me turn on my pointers. Associate with a weight, and you go through all the way. You got some prediction, and then you compare the prediction with the actual value using a loss function. And from the loss function, you end up with some sort of loss score. And then you use the optimizer to update the weight using this loss score, and then the weight come back here. And you keep repeating this process until maybe the weight converge. So that's the gist of it. Now, as far as the data and layer, we all talked about this in last video, so we're not going to repeat it too much here. Keep in mind that the number of layers can be different depending on the application that you have. And for the graphical representation of it, keep in mind that the superscript is a layer number, and the lower subscript is the node in the layer. And the Z is the responding value after the linear transformation, and the A is after the nonlinear activation function. Okay, let's talk about loss functions here. Very important. And you might heard of loss function to many names: cost function, objective function, error function, so on and so forth. But all it does is trying to measure how well an algorithms model the data. And this loss function need to be minimized during training. So we have seen a few type of loss function before in previous classes. Maybe you would see square loss, log loss, hinge loss, in support vector machine, entropy, and other type of loss. Now, for regression tasks in neural net, we use MSE or square loss. Right? It's a very typical square loss to you, right? Just a square of the difference between the predicted and the actual value. And for classification tasks in neural net, we can use cross entropy or log loss to evaluate the network output. And typically, if you use the softmax function like I talked about last time, your output going to be a probability distribution. So it works really well with cross entropy. And cross entropy for binary case is calculated as these formulations here. And for the multi-class classification using one hot label, it can be calculated under this formulation. And the thing about this cross entropy is that it will increase, the loss will increase if the predicted probability diverges from the label. So by the way, cross entropy in binary case is the same as log loss. So this graph shows it in the binary case, and you see if the label is 1 and my predicted probability really close to 1, then my loss should be 0, right? That makes sense. Now, if the probability of predicting 1 reduces or not as high as 1, this log loss going up as you have lower probability of predicting 1. So that's reflected correctly how the loss function should drive the higher probability, hopefully through the iteration. But that's your loss function. Now, the next thing we need is, and the final thing we need is an optimizer. And an optimizer is used to learn the network parameters by minimize the loss of the error functions. And there is many ways you can do this, and we're going to talk about a few of them. But remember, when you train the network, what you're doing is that you trying to determine the value of the network parameter so that the error is minimum. Right? So we've seen before gradient descent, classic machine learning, mini batch, gradient descent, quadratic programming in case of SVM. For neural network, mostly we will use gradient descent and various variants of gradient descent. So we're going to talk about these optimizer in the next module, including momentum, RMS props, and atoms. But today, though, we will look into a special type of gradient descent algorithm called backpropagation, and to compute the gradient of the network parameters. So here we go, backprop. So back in 1986, Rumal Hart and his group proposed a groundbreaking article, backprop, and that changed the face of deep learning. That called connexionism at the time, but it's kind of bring it back in the 80s and sort of a first renaissance after the AI winter. And it consists of 3 steps. Forward pass is when you're feeding an instant to the network, and then you pass the signal through the network from the input layer to hidden layer to the output layer, and you calculate the output for every neuron, and then measure the errors at the end of the output layer using the loss function. After that, you're going to pass the signal backward from the error in the output. You're going to measure or propagate the error contribution back to every single neuron in a previous layers. And during this pass back, as you will see in the next few slides, that the error would be contribute to different parameters in the network. And then the third step is gradient descent. And without a lot of explanation here, you just run the gradient descent on the connection weight using the errors that measure in step 2. Now, in order to understand or represent this backprop a lot more precisely, we had to introduce you to the computational graph language. And it may feel intimidating. It's really not. You can think about it. It consists of operation between 2 nodes in the graph, one or more variable, and if the function is complicated, it can be break down into simpler operation and then composing them together. Right? So we've seen this actually many times before. May not call it computational graph, but here we go. So if you want to calculate z is x times y, this is a graph to represent it. You have x node, y node, and the operation in multiplication. You have a result output as z. You can do this for vector as well. So you have x vector and w vector. You can do dot product to having a response value, and then you can add another value here. In this case, b is a bias term, and you can add them together. And then from this one, you can go to a nonlinear activation sigma here to get your output. Right? So you can build even more complicated graph with matrix multiplications using different activation function and other. You can build it all in. So it's really a really neat tool to represent the thought process and the computational process in deep learning. So we're gonna go back and use it once in a while, right? Another thing want to talk about, a touch on simple to simple derivative. And if you can think about it, this is a computational graph to calculate going from w, go to some function to x, go to some function to y, go to some function to z. Now, what we're going to do in the neural net, we want to calculate the derivative, like the gradient. So what we're going to do is, if you want to calculate the partial derivative between of z with respect to w, so z is here, but w way down here, right? So you have no direct way you can compute the gradient there, or the partial derivative there. But thanks to calculus, we have change rule, and change rule said that you can calculate the derivative with some variable by establish a chain from one variable to another variable that you want to take the partial derivative with respect to. So dz over dw here going to be partial with partial y, and then a partial y over partial x over partial x over partial W. So you can see here it's established a chain with Y and X in between. And this is the way we can effectively calculate derivative of any node in the computational graph if you know the function that lead from one node to the next. So it's pretty neat tool. Another thing I want to mention is that notice that the FW and derivative FW are computing repeatedly. So using this computational graph, maybe we can figure out a way to store them once and use them for multiple times, right? Which is very important in computer science. And another really nice thing about this simple to simple approach is that we can derive or describe the derivatives without specifying when exactly the operation can be complete. And let me show you how that derivative can take place. So for the y, you can derive with the partial derivative, of z with respect to y. Right? Same thing, you can do partial derivative with of y with respect to x, and then partial derivative of x with respect to w. And with change rule, the next operation is quite simple. That is establish a change. It's just the product between these partial derivative, and then you change again to find the partial derivative between z and w. Right. A quick reminder, though, why we're trying to calculate all these partial derivative. So partial derivative by definition is calculate the rate of change of one variable with respect to the other variable. So what happened here, if I calculate this one, then I know how much z will change if w change a little bit, right? Just think about it like the mountain example that we see earlier. If the direction is, I have 8 directions I want to go, that's maybe multiple setting of w, and the z is I want to descend the mountain or go and lower. So basically what I look around and I figured out which way should I take or what w value should I use here so that the change in z is the greatest perhaps, right? So this derivative, partial derivative, help you trying to do that. If I wiggle w a little bit, what happened to z, right? And you can do that for any variable in the computational graph, right? So that's important. I want you to know that because next we're going to look at how you apply this into the neural net. Okay, so training a neural network, you see this graphical representation of the neural net before. This have 2 layers, and each first layer have 2 nodes, first layer have 4 nodes, second layer have 2 nodes. And it's kind of nice representation and give a good visual representation of the visual of neural net, but it's not very difficult to compute because the weight now represented the arrows, and you have a lot of different nodes here. So a better way to represent this representation, and this is equivalent, is using the computational graph, right? So for the computational graph, all this x going to be represented by vector x. We have the weight w to see all the arrows here. So maybe a quiz, what the dimension is w1's here, right? And then the f represent the linear transformation or the weighted sum to a response value, and then you apply some activation function sigma here to obtain a1. Again, this z and a is now vectorized, and then you do that to the next layer. Apply a linear transformation, then with weight w, right? You have another weight here because you see arrows here, and then non-linear activation. And then finally, when you produce the predicted values here, you're going to compare it with the actual label through some loss function. So the loss function can also be represented in this computational graph, and you use MSE to calculate the loss functions here. So that is your computational graph. Now we're going to go a little bit deeper in here, trying to calculate different steps of the backprop. So number 1 step is the forward pass. So all I want to do is compute the loss function, right? So I have my data x and my weight w. I'm going to combine them into z using a linear transformation or w matrix multiplication, wx. And then I will use a nonlinear transformation, sigma, to compute a1 from z1. Next, I'm going to have different sets of weights here because I will do another affine or linear transformation to calculate z2 or the z of layer 2, right? And then again, nonlinear transformation to compute A2. Now from A2, I'm going to introduce the predictive value of the network. And from there, I can calculate the network error or the value of the loss function by comparing it with the label y. So here we go. We have a loss function, which is MSE, calculate the errors of the network. And that is our forward pass. So far, so good. Now, the backward pass is slightly more complicated because you have to take the partial derivative, right? So what you can think about it here is for each step, I want to measure how the change of the current node affect the node after it, right? So for A2 here, I want to calculate how A2 can affect the loss function, right? So that by taking the partial derivative of L with respect to A2, I can see how A2 affect the loss function, right? So I take partial derivative L with respect to A2. You do some calculus here. It's going to be just the difference between the predictive value and the label, right? I'm going to do the same with my other node, and keep in mind what each of these nodes does, and you can calculate it fairly quickly. Is you want to just see, okay, if I want to change the value of Z2 a little bit, what happened to A2, right? So that is what partial derivative here, and you can take the derivative of the non-linear activation function sigma. So this is sigma prime for that, right? And then you can calculate partial derivative of W with respect to the node after it, which is Z2. So W here, a rate of change of W with respect to Z2, and so on and so forth. You can calculate all of these partial derivative from one node with the node after it, right? So far so good. Just do some calculus, partial derivative, no problem. The next step is quite important. The next step is to apply change rule. And we just see change rule slightly a couple of slides ago, but now we can combine different partial derivative here to apply to construct a change rule, right? So we started with this change. We have, what we're really interested in is the rate of change or the partial derivative between the loss function and a variable, a node, right? So for this node, we really don't have the rate of change between the cost function and itself yet. So what we're gonna do is gonna try to create a chain to do this to accomplish our task. So the rate of change of the loss function with respect to Z2, which is what we want to calculate, we can compute it by just establish the chain from L to A and then A to Z, right? So you can see the change rule in effect here, and then I can compute this by computing these two, right? These two derivatives. Now I know how the chain in Z2 can affect L, right? So here, how I see the chain in A2 affecting L. I do that again for my A1, for my Z1. It's really the same principle. Now, all this value is important, but you know what even more important value? It is the parameter of the network, the W that I haven't mentioned, but you can calculate W pretty much the same way. With this W, it basically just a chain between its derivative and the partial derivative of Z2, right? So the partial derivative of L over W2 going to be the chain L to respect to Z2 and Z2 with respect to W2. And we know these both of these quantity already, so we can calculate that rate of change without any problem. Change rule is really nice in this case. And if you really want to extend a really long chain back to the original rate of change or MSEs here, you can establish slightly longer chains here. But with the computational graph, you can see how that turned out really nicely. Look at it. So you can go here and go there. Right? And then with weight W, which is the other weight of the network, you can also use change rule to calculate it by using a partial derivative time the rate of change with respect to Z1 here. And if you need to establish the chains again, you can expand this out. So from L to A2, A2 to Z2, Z2 to A1, A1 to Z1, and Z1 to W1. So you can see how the whole chain effect from the change in the cost function all the way to the change in W1, network parameter at layer 1. So this is a really nice computation that you can see that make things easier for you to grasp hold. It's very important to understand. Now, let's put everything together in the backprop algorithms. So first, you initialize the network parameters, W1 and W2, to random value. Or we have other really neat way to initialize the network. We will cover it in the next modules. So we're going to repeat until converge. Pass the signal forward to compute the loss function all the way through. And then pass the signal backward to compute the gradient, right? So we just show you how to compute the gradient of W1 and W2. So you should follow the same procedures to compute that. And then the last step is the gradient descent, or update the network parameter. And the way it does is very similar to gradient descent that you see earlier. You have some value of the network. You're gonna go on the opposite direction of the derivative because you want to go downhill, right? Remember, you want to minimize the cost function, so you want to go the opposite direction of the gradient or the partial derivative here, and with some rates of change. So that's, you go downhill, opposite direction, so that's minus sign, rate of change, gradient. And so every time you're gonna wiggle all this value of W1 and W2 a little bit so that the errors go down, right? Now, very powerful note here. You're not changing one parameter at the time. You're changing all the parameters, all the weights in matrix W's at the time. And every time you change it, the errors keep going down, keep going down. So you keep repeat until the error will not go down anymore. And when is that? Well, hopefully it will arrive at the minimum errors, right? So that is backprop algorithm. Very cool stuff. You can actually go check it out at the TensorFlow playground. You can establish a bit of a experiment for yourself. I would definitely encourage you to do it. And we're gonna have a few software library that can use, and I'm very excited to gonna introduce that to you until the next video. But until then, take care.